from a graphical perspective with exponential functions, and then I'll formally define them on the next page. And then I was thinking a little bit more about it this morning. I think I'm going to kind of bounce around a little bit just to make the flow a little better with the presentation of topics. In the section 6.3 that's in our textbook, it's just kind of all thrown at you. So I try to follow logical order as best as I can. And after I was thinking it over, I think we might just kind of bounce around just a tad in this section, just to make the continuity of topics as best as possible. All right, so we are going to take a look at exponential functions. And we're going to start by graphing a few. First one that we're going to graph is 2 to the power of x. So what makes this an exponential function is that you have a fixed base. Okay, 2 is a fixed number. That's not going to change. But what is changing is the exponent that's on this 2. And that's basically the tall tail sign that you're working with an exponential function, is that the function involves an exponential expression where the variable is part of the exponent. And how this works is that whatever x value we choose, we're just going to make it a power on 2, and then we'll simplify if necessary. And this is also a chance for me to explain why something like 2 to the 0 is equal to 1. All right, we can kind of see evidence of that in the table once we fill it out, or along the way of filling it out. So I do have a table of values already prepped for us a little bit. The x values are going from -3 to +3. And I'm going to start with the x value of 1, just to kind of prime us for this. When x is 1, the 1 is going to become a power on 2, and that gives us 2. I'm going to next do x equals 2, in which case we would make 2 a power on 2, which would give us 4. And then for x equals 3, we'd have 2 cubed, which gives us 8. Now, the reason why I started with this part of the table is just so that we could recognize a pattern between the y values, specifically 2, 4, and 8. Is there any pattern that you can recognize which takes us from one y value to the next y value? Multiplication by 2. So to get from 2 to 4, we could multiply by 2. And to get from 4 to 8, you can multiply by 2. So multiplication by 2 is how you get from one y value to the next as you increase in the x values. But what rule would take us in the other direction? So for instance, if we were to start at 8 and then go to 4 and then go to 2, you would have to do division by 2. So to go from 8 to 4, we divide by 2. To go from 4 to 2, we divide by 2. And we're going to continue in this trend to get the y value for when x is 0. All right, any offers on what that might be? It would be 1. We could also continue with division by 2 to get the y values for when x is negative. So when x is -1, we could take 1 and divide it by 2 to get 1/2. It's also worth mentioning that you can use an exponent property to simplify 2 to any negative powers. So for example, 2 to the power of -2, we can change that -2 exponent to a positive exponent provided we reciprocate. So that'd be 1 over 2 squared, which gives us 1/4. Or we could divide 1/2 by 2. 2 to the negative 3 power. If we wanted to make negative 3 positive, we'd have to do 1 over 2 cubed, giving us 1/8. All right, so you can continue with division by 2 going up the ladder, if you will. Or, if you want to go down the ladder, the pattern would be multiplication by 2. All right, so let's say we knew that 2 to the negative 1 is 1/2, then, multiplying 1/2 by 2 gives us 1, which is, extra verification that 2 to the power of 0 is 1. Is this all making sense so far? All right, so I'm going to form ordered pairs for all the points that we just made, and I'm going to use the decimal equivalent for these fractions, just so that it's a little easier to plot. So when x is negative 3, y is 1/8, which as a decimal is 0.125. When x is negative 2, we get 1/4, which is 0.25. When x is negative 1, 1/2 is 0.5. And then we get some whole numbers for the y coordinates. 0, 1, 1, 2, 2, 4, and 3, 8. Let's go ahead and plot these points. I like to start with 0, 1. And then what I'm going to do is plot the points that fall underneath it in the table. So 1, 2, 2, 4, and 3, 8. Now, if we had used x equals 4 in the table, what do you think the y value would be? So if we used 4, we would do 2 to the 4th power, or you could continue the pattern of multiplication by 2 to do 8 times 2, which would give us 16. And I didn't include 4 because we would be off the map with that. And that's kind of typical of exponential functions. When you go in one direction in the along the x-axis, you're going to have one end of the graph that skyrockets to positive infinity. That would be on to the left or right of the point 0, 1. In this case, to the right of 0, 1, we have points that are quickly going up to positive infinity. But to the left of 0, 1, there's quite a different behavior going on. So if we plot negative 1, 0.5, oops, we'll have that point right there. And then negative 2, 0.25 is going to be even lower than that. And then negative 3.125 is going to be even lower than that. And so to the left of this point, 0, 1, the y-intercept, we're having points that are getting really, really close to the x-axis. But believe it or not, these points, although they get closer and closer to the x-axis, they'll actually never cross or touch it. And doesn't that kind of sound familiar? Didn't we kind of talk about a concept like that in chapter 5? So there's exactly, yep, there's an indication of an asymptote here. So I'll flesh that out in just a second. What I'd like to do right now, though, is help you guys connect these points. So I'm going to start at the y-intercept of 0, 1, and then I'm going to connect I'm going to connect the points to the right of it in a curvy fashion, and then just indicate that that end goes up to positive infinity. And it goes there quite fast. But to the left of 0, 1, we're going to have an end of the graph that approaches the x-axis without crossing or touching it. So due to that fact that we have an end of the graph getting close to the x-axis but never crossing or touching it, that qualifies the x-axis as a horizontal asymptote. And the equation for it would be y equals 0. Okay, so one end gets closer to the x-axis while the other end goes up to positive infinity. And that would be an example of an exponential function graph. Ta-da! Any questions so far? Oh, it's going to get even cooler. You just wait. Let's move on to another exponential function. You'll notice that what we're raising to the power of x is the reciprocal of 2. In other words, we have 1/2. And we'll see that based on this value, it's going to change the direction of the ends. So I'm going to give you folks an opportunity to come up with the y values for this table. And once you come up with the y values, see if you can plot the points and then connect them, much like we were doing with the last problem. All right. And in just a couple minutes, I'll flesh out my y values, and then we can kind of compare notes with each other. All right, I'm going to flesh out my y values. 1/2 to the 0 is 1. 1/2 to the first power is 1/2, or 0.5. 1/2 square, you square the top and bottom to get 1/4, 0.25. And then 1/2 cubed is going to be 1/8, which is 0.125 in decimal format. When the exponents are negative, you actually get whole numbers. So for instance, if we took 1/2 and raised it to the -1 power, we could make that -1 power a positive, provided we reciprocate the fraction. So we end up getting 2 to the +1, which is 2. 1/2 to the power of -2 converts to 2 squared, which is 4. And then -3 will give us a y value of 8. So here are our points: -3, 8, -2, 4, -1, 2, 0, 1, 1.5, 2, 0.25, and then 3, 0.125. And there's a trend within the y values. If we start with the y value of 8, the very top y value, to go from 8 to 4, that's division by 2, which is the same as multiplication by 1/2. You can multiply 4 by 1/2 to get 2. You can multiply 2 by 1/2 to get 1, and so on and so forth. And if you go in the reverse direction, you're going to divide by 1/2, which is the same as multiplication by 2. So hopefully you're getting the sense that with exponential functions, there's this constant usage of multiplication, and what we're multiplying to get from one y value to the next is the base that's involved in our exponential function. Okay, so our base here is 1/2, and to get from one y value to the next, that's exactly what we use. We use multiplication by 1/2. So anyway, let's go ahead and plot these points. -3, 8, -2, 4, -1, 2, 0, 1, and yeah, Timothy, I think that's a great way of describing it. It is kind of the reverse from the last problem. You'll notice that to the left of 0, 1, the end is now going up to positive infinity, whereas to the right of 0, 1, it's getting close to the x-axis. So I'm going to connect those points that are to the right of 0, 1. And what's happening is these points are getting closer and closer to the x-axis without crossing or touching it. And then to the left of 0, 1, we have the other end of the graph going up to positive infinity. So since this end approaches the x-axis without crossing or touching it, that qualifies the x-axis as a horizontal asymptote again. And the equation for it is y = 0. Okay, so did you guys come up with a similar graph? All right. Very good. Has anybody here ever heard of the number e? I didn't misspeak, by the way. E is a number in math, unfortunately. Well, E is kind of an interesting creature. E is a number much like pi in that it's an irrational number. That is, the decimal values go on and on. They don't stop. And there's no overarching pattern to them. And we're going to work with this number quite a bit moving forward. And the closer we get to the end of Chapter 6, the more often we use it. But I uploaded some resources in the 6.3 folder. One resource is a PDF scan of an article I wrote for the Schoolcraft newsletter that they used to put out. And I wrote that back when I was a student in 2005. And it was an article I wrote dedicated to one of my calculus instructors. She had this question about E, and it just kind of motivated me to do some digging and come up with a little bit of the history on it. So if you're looking for some light reading to help you quickly fall asleep at night, then you can go ahead and or consider reading the article I wrote. Another resource is a video I made where I derived this number numerically using a special type of exponential function. But what's interesting about this number is that it kind of shows up everywhere, obviously in math, but it shows up a lot in a lot of the different sciences like physics and biology and chemistry, and even some of like those soft sciences. We find the number E showing up, and E, I'll make a little note down here. Since E is irrational, when we work with it in practice, we use kind of like a decimal approximation of it. And one decimal approximation of E is 2.71828. And I normally don't use all those digits, but I flesh them out just to give a higher level of accuracy. You don't have to remember this value, but just at least be aware of it. Fortunately, because it's not a very easy decimal to work with, our graphing calculators have E programmed into them. And there are a couple of ways that we can access E on the graphing calculator. And I'd like to show you how to do that so that we can fill out this table with approximate Y values. So E, there are lots of schools of thought on that who came up with the number E. The assignment of the letter E to the number is said to be after a mathematician named Euler, which is spelled E-U-L-E-R. It's really weird how we say it, but in my research, E was kind of the result of a thought experiment. So I'll direct you to the article I wrote up, and I think the article will help you answer that. For now, let's see how we can punch this into our graphing calculators. There are a couple ways to do it. Both ways involve hitting the second button first. And the first route that we can take to access E is to press the divides button. And then you can hit the caret symbol. And let's say we want to just figure out what E to the first is. Type in 1 and press enter. And there's an even further decimal approximation of it. This is a little deceiving because it looks like there's a pattern, but as you go further out with the decimals, it starts to get a little more random and chaotic. Now E squared, I'll show you with the second route that you can take. So let's press the second button, and then in the first column next to 4, there should be a key that says ln. Let's press that. And I like to use this one more so than the first route because it puts me in the exponent. And if you have a TI-83, you're probably seeing like a caret symbol next to this with a half set of parentheses. Regardless of what we're seeing, whether you have an 84 or 83, let's go ahead and type in 2 and press enter. And so E squared is approximately 7.39-ish. Okay, let's do one more together. Second ln, E cubed, and we'll press enter. And we're looking at 20.09-ish. So let me log these down in our table. E to the first, and I'm going to round to 2 decimal places, is approximately 2.72. E squared was approximately 7.39. E cubed, approximately 20.09. And I'm going to give you the next minute or so to figure out the other y values using your graphing calculator. And once that's finished, we'll form the points, plot them, and we'll kind of compare and contrast this graph with the previous two. All right. All right, so e to the 0 gives us 1. E to the power of -1, if we round that to 2 decimal places, I got roughly 0.37. E to the power of -2 gets pretty small once we go further in the negatives. All right, so go ahead and check your values against mine. Let me know if you're getting anything different. You guys coming up with these values then? Let's go ahead and plot them. I'll start with 0, 1. 0.14 for negative 2. Oh, let's see. All right. I'm not sure what happened there. Better double check e to the negative 3. Oh, I'm not sure what I had done then. Okay, so 0.14. There we go. How do those look? It's probably mine that's broken. No, I'm just kidding. All right. Well, let's go ahead and plot these now that they're fixed. I'll start with 0, 1, and then 1 and approximately 2.72. So what I do is I just get a little bit underneath the y value of 3, just to eyeball it, and then 2, 7.39. So I'm going to go to 2, and I'm going to go a little bit past the y value of 7, and then we can't even plot 3, 20.09 on this grid. But this will probably suffice. It'll help us see the shape of the graph. Negative 1, 0.37. So I'll go a little bit above the x-axis at negative 1, and then I won't go as high with negative 2, and I won't go as high with negative 3. And basically, it kind of resembles the graph of 2 to the x, in that the right end of the graph skyrockets to positive infinity, whereas the left end of the graph approaches the x-axis. And speaking of, this end of the graph will approach the x-axis but never cross or touch it. So as we go further in the negatives, the y values do get extremely small, but they actually never reach the y value of 0. So that's, kind of a hallmark quality of asymptotes, right? But knowing that can be quite helpful, especially when we have to graph these things using transformations. And it's also an indication that there's a horizontal asymptote. And there we have it. So let's get to the official definition of an exponential function, and then we'll look at a couple of application problems involving them. Then we'll revisit these graphs, but in the context of transformations. So the way our author defines an exponential function is a function that has the following format. Let's write capital C times a, and in the exponent of a, we're going to put the variable x. Yep, we're going to classify that or generalize that once we get back to graphing. So yeah, there's actually quite a few patterns within these things that are really helpful to know, and we'll definitely qualify those once we're finished with the applications. So what makes this an exponential function is that we have an exponential expression. In the base of the exponential expression, we have what's called the base, sometimes referred to as the growth factor. And I didn't include it in the remarks, but in certain cases, it's also referred to as the decay factor. And basically, the base is the number that we multiply each of the y values by to generate the next ones. And obviously, we have a variable in the exponent of a, and an exponential expression of this form, where it's a number raised to a variable expression, is what makes it an exponential function. Now, if you're wondering about this letter C, it does have some significance, and it's sometimes referred to as the initial value. Okay, there are other ways of defining exponential functions, and actually you'll see that once we come back and do transformations. But for now, the author keeps it pretty basic. He allows for a number in front of the exponential expression. And I think, he goes with this version because when we solve application problems, this variable c has some pretty good information tied into it. So c times a to the power of x. And that's a good segue to page 5, which, as I mentioned, we'll do a little bit of skipping around here. So we'll look at applications next. And the reason why I want to do it this way is because after defining that format of an exponential function, it might be helpful to see like some specific examples of exponential functions, which is exactly what we're going to see in these next two examples. Now, exponential functions, they give way to what's called exponential growth and exponential decay. And lots of things in the real world follow the patterns of exponential functions. A lot of things grow exponentially, such as bacteria or populations, and a lot of things decay exponentially or, depreciate. So for instance, when you buy a car, you probably know what happens as soon as you drive it off the lot, right? The value of the car drops significantly, and it continues to drop significantly, the further a long time goes by. Certain medicines and bloodstreams decay exponentially. And I uploaded some videos. They're in the section 6.3 folder with some other examples of exponential growth and decay. But investments display exponential growth. And then there's one in there that I found yesterday that involves a fidget spinner. And so like the speed of the fidget spinner, it decreases, in like an exponential decay format. Radioactive decay is another application of exponential functions, and there are just so many more. So these things are quite important, and they're very helpful to understand in a lot of facets. So in our first application problem, we're going to look at an exponential function that models the price of a specific kind of car, a Honda Civic EXL. And it says here the price P in dollars of this kind of car is that is X years old is modeled by P of X equals 25,495 times 0.90 to the power of X. So thinking back to our definition of an exponential function, 25,495 is our value of C, and then 0.90 is our value of A. Now keep in mind that C is the initial value, and in this particular function, C is 25,495. In this application setting, that would represent the initial value of the price, or stated differently, initial price. So this is the price of the Honda Civic should no years go by. Okay, so this is what the price starts out as. In part A, we want to figure out what the price should be if the Honda Civic is 3 years old. So it says here, how much should a 3-year-old Civic sedan cost? And this represents a specific value of X, namely X equals 3. So you probably know what we're going to do here. We're going to plug 3 into our function, and then we can use our calculators to grind out the price. So P of 3 is going to be 25,495, and I usually put the base in parentheses because sometimes the value of C has a decimal and it can get confusing. So I'm going to put 0.90 in parentheses and then put a power of 3 on it. Now let's go to our calculators. and we'll type in 25,495, and then we can write or type in the parentheses 0.90. Let's close them off. And then to put a power of 3 on it, we'll hit the caret key, press 3, and let the calculator do its magic. So just after 3 years, the price drops by roughly $7,000. So it's a pretty steep drop for such little time. But that would be the price. And let's round it to the nearest penny. So 18,585 and 86 cents. Did you guys come up with the same value? Rock on. All right, well, let me have you guys take care of B, and once you have the price, if you want to type it into the chat, that'd be appreciated. All right. So yeah, for part B, we're going to look at the x value of 9. So we'll do P of 9. And I'm getting the same value. Thanks for typing it into the chat. 9,877.29. Wow, that's quite a steep drop there. So this type of function that we have here would be an example of depreciation, or which is kind of a special case of exponential decay. In other words, as time goes on, the initial value decreases in an exponential fashion. So to give you an idea of how that works numerically, I'm going to make a little table here, and I'll have x for the first column, p of x for the second column. And we'll start with an x value of 0. So when no time, or when no years go by, this would correspond to the initial price of 25,495. It wasn't asked for it in either parts A or B, but we could come up with it a couple of ways for an x value of 1. So what would the price be after 1 year goes by? Well, we could plug 1 into the function, or what we could do is use the base A and apply it to the 25,495. So keep in mind, to get from one y value to the next, we do repeated multiplication, right? So for instance, to figure out the price after 1 year, we could multiply this by 0.90. To get the price after 2 years, we could take whatever we get here and multiply it by 0.90. And then to get the value For 3 years, we could take the most recent price corresponding to 2 years, multiply it by 0.90, and that should land us at our value of 18,585.86. And you can continue doing this for as long as you want, theoretically, and over time, the price of the Honda Civic just keeps dropping and dropping and dropping. Now, the main reason why I'm having this discussion is because I'm going to add a part C in here. And the part C question is going to be this. What does the value of A mean? And to answer this, let's go back to this table and see what the value of A does. So we start out with the initial price of $25,495. After 1 year, the price is now 90% of that. After 2 years, the price is now 90% of what it was after 1 year. For 3 years, the price is now 90% of what it was after 2 years. And so as the X values increase, for each additional year, you're paying 90% of the previous year's cost. A more succinct way of saying that is that the price drops by 10% each year, right? Because if you're only paying 90% of the original price after year 1, then the only way that's going to happen is if you drop the price by 10%. Does that all make sense? So in our problem, A is equal to 0.90, and what this implies is that each year the price decreases or drops by 10%, and that would be the significance of A. Or you could form it the long way, where for each additional year you're paying 90% of the previous year's price. That's a little too wordy for me, so I would say each year the price decreases by 10%. I know, right? Imagine having to say that over and over. So if this is all gelling with y'all, let me give you a problem to work on page 6. It's not the most exciting kind of example here. It's a little nihilistic, and I kind of struggle to put problems like these in the notes, but I also find it a little bit interesting in the sense that math can be used to model these sorts of situations. And in a sense, I find math helpful in a perspective like this, because it can kind of help us do some predicting and make informed decisions about how to handle things like people that have advanced stage pancreatic cancer. It turns out that you can model the survival percentage using an exponential function, which is kind of interesting in my opinion, although the context is quite sad. But I'm going to have you give this a shot. It says here the percentage of patients P who survived 2 years after initial diagnosis of advanced stage pancreatic cancer is modeled by the following function. Capital P of t equals 30 times 0.3t. Based on our definition of an exponential function, the initial value is 30, and our base is 0.3. and the independent variable here is t instead of x. But you're going to operate with this much like we did in the last example, and I'm going to have you take the next couple of minutes or so to see if you can work out parts A and B, and then I'll go ahead and go over the answers with you, and we'll go from there. Lickety split, there we go. Yep. So for part A, you'll do P of 1. It says here 1 year. Okay, so that's T equals 1. You'll do 30, and then I'm going to write parentheses, 0.3 to the power of 1. Yep, you get 9. So in this context, the 9 represents a percent. So after 1 year, so 1 year after initial diagnosis, 9% of patients survive. It's pretty startling, right? After 2 years, so that's T equals 2, it drops even lower to 2.7, which in this context is a percent, so 2.7%. So only 2.7% of patients survive 2 years after the initial diagnosis. That is hashtag cray. And I'm going to add a part C, much like in the last problem. I'll say, what does A mean? What do you guys think? It is decaying, yep. So as time goes by, the percentage is decreasing. Okay, so that's exponential decay. Now keep in mind our A value is 3, or 0.3. Which the base here of 0.3, this isn't a specific percent, although we could convert it to a percent by moving the decimal 2 places to the right, 30%. And basically, as each year goes by, you know, the survival is 30% of the previous years. Or stated more succinctly, each year, the percent of patients surviving decreases by 70%. Okay, so there's a 70% drop each year, and the 70% drop is based on the previous years. Okay, so it's, you know, when we're multiplying repeatedly by 0.3, by 0.3, by 0.3, you know, effectively we're generating percentages that are 70% of the previous percent. All right, so that's what's going on here. And do you guys have any questions about anything we've done so far? All right, so let this all sink in. We're going to take a break. When you come back, we're going to revisit the graphs and do some transformations, and then we'll finish class off with some equations. All right, so I'll see you guys soon. All right, you guys ready to jump back in the saddle? Just gotta double check that I'm recording. I forgot to record yesterday's session, so all right, we're good. Sorry, sorry if I seem a little foggy or sluggish today. I haven't told you guys this, but I'm on immunosuppressants for an autoimmune condition that I have, so I had to take my medicine a few days ago, and it kind of makes me a little foggy. So, if anything isn't, clear, just feel free to let me know, and I'll be more than happy to divulge and clarify. So we're going to revisit the graphs of exponential functions. We'll first do so in sort of a general setting, and then once we're familiar with how these things go from a basic viewpoint, we will apply some transformations. All right, so I got some tips and tricks for you on that. But let's first see how the base of the exponential function affects the graph. So in the words of Meghan Trainor, it really is all about that base. You guys remember that song from years ago? All about that base? Oh man, now it's going to be stuck in my head. So sorry if it gets stuck in your guys' head the rest of the day. But let's take a look at a situation where the base is greater than 1. This would represent exponential growth, by the way. So things are increasing over time. When the value of a is greater than 1, one end of the graph, the left end of it, starts out close to the x-axis, and it increases, goes through the y-axis, and then takes a sharp turn up and heads to positive infinity. The y-intercept, or the spot where this graph crosses the y-axis, is going to be at 0, 1. And I think somebody mentioned in the chat that all the tables or all the graphs on page 1 had the point 0, 1 in common. And that is a fantastic observation, because provided there are no transformations, that'll always be the case, regardless of what your base is. So if a is greater than 1, it goes through 0, 1. And we'll see in just a minute or two that when a is less than 1, it also goes through 0, 1. But another point that I want to give to you that's on this graph, which will be helpful for accuracy in our transformations, is 1 comma a. Okay, so if we raise a to the first power, we just get a. Now there is the horizontal asymptote, which goes along the x-axis, provided there are no vertical shifts. And the equation for it is y equals 0. And another thing that I want to provide to you on this diagram is what I like to call the 1 unit gap. And basically the 1 unit gap is the distance between the y-intercept and the horizontal asymptote. Kind of looks like a cactus. I'm going to call that the 1 unit gap. That's super helpful for when we sketch with transformations. Now, because one end of the graph continues to the right, going up to positive infinity, and the other end continues to the left, going to the horizontal asymptote, these ends don't stop. And because of that, and the fact that everything is fully connected, the domain is going to be all real numbers. But the range is going to be 0 to infinity with parentheses on each of these. I know it looks like the graph might hit the x-axis, but it actually never does. Okay, so that's why parentheses on the 0. And as we look at this graph from left to right, okay, everything is increasing. And that's what it says here, increases from left to right. And for this part where it says contains the point, I'm just going to include 0, 1, although it does also contain 1 comma a. And then the equation for the horizontal asymptote is y equals 0, aka the x-axis. So on the last page, we had two functions that looked very similar to this. f of x equals 2 to the x, and then f of x equals e to the x. Each of those bases are larger than 1, which is why their shapes look like this. Now when the base is less than 1, we get exponential decay, meaning that things decrease over time. Case in point, the left end of the graph is the part that went to positive infinity, and then the right end of the graph was the end that approached the x-axis. As I mentioned a minute or so ago, both graphs, provided no transformations, will go through the point 0, 1. And in this case, 1a is to the right of 0, 1 still, but a little bit lower than the y-intercept. The x-axis serves as a horizontal asymptote still. And there's also the 1 unit gap between the y-intercept and the horizontal asymptote. Okay, so in this case, the left end goes up to positive infinity, whereas the right end approaches the x-axis. Now, what's fascinating about this is that basically everything in terms of the specs, the domain, range, and so on and so forth, most everything is the same, with exception to the behavior. So with a graph where the base is less than 1, we have a graph that decreases from left to right. But other than that, the domain will still be all real numbers. The range, 0 to infinity, contains the point 0, 1, and also 1a, but I'll just write 0, 1. And then the horizontal asymptote is y equals 0. So from page 1, we saw a graph like this, and that was for f of x equals 1/2 to the power of x. And clearly, 1/2 is less than 1. And even if we had a different fraction, as long as it was less than 1, the shape would still look like this. So lots of similarities, and it definitely makes life easier knowing that the shape of your graph is basically based on the base. And how many times can I say base in one sentence, right? But anyhow, this is all true, provided there are no transformations. So what happens when there are transformations? I'd like to go ahead and address that next. So usually when you have to sketch an exponential function using transformations, the function takes on a little bit of a different format than c times a to the x. And the format that I'm going to give you is the following. A, and in its exponent, the expression x minus h, and back down on the ground at the tail end of this, plus k. And in some cases, we might have some negatives involved. I would say the most common place for a negative is in front of the exponential expression, although it could be in front of x, which we're going to see an example of that in just a few minutes. But usually with transformations, your exponential function has this format, okay? Sometimes with the negative, sometimes without. And there's a particular order that you want to follow when you do the transformations. You always want to start out with a base graph, much like we did back in Chapter 3. For Chapter 3, we looked at the library for it, but in this chapter, for exponential functions, we're going to look at the base. Okay, so that's the first thing that we do, is we examine the base. If the base is larger than 1, then what I'm going to do is include a base graph as a dashed version of a to the x. If it's less than 1, then the direction of it changes. If there are any negatives in front of a, that would be the next thing that we plot. And this is kind of a situation where it's on the exterior, and we know that negatives cause reflections. In this case, if it's in front of A, it's going to be an x-axis reflection. And then in the exponent, if we add or subtract directly to x, we can take some wisdom from chapter 3. This would be the third thing that we do, and this is going to be a horizontal shift. And remember, with horizontal shift, you got to think opposite. So if it's subtraction, we move to the right, but if it's addition to x, then we move left. And last but not least, we look at what we're either adding or subtracting at the tail end of the function, which would represent the vertical shift. Got to remember to write F when I write the word shift. And for vertical shift, you can think normal, i.e., if you're adding, you move up. If you're subtracting, you move down. But what's really cool about this vertical shifting is that it's tied into your range and your horizontal asymptote. So I'm going to do a couple bullet points for this, okay? We can actually get the equation for the horizontal asymptote based on the value of k. And the horizontal asymptote is going to be y equals the value of k. And then for the range, it's going to be one of two things. The range will either be negative infinity comma k, or parentheses k comma infinity. Okay, so just some tips and tricks. And this is the order that we want to follow as best as we can. You can do, once you get comfortable with the skill, you can mesh together the horizontal and vertical shift with each other. But if this is the first time ever doing something like this, I recommend including as many graphs as possible, even though it's going to get a little bit messy. So we just got to be really clear about our work, and that takes us to our next page, where we're going to do just that. We're going to sketch each graph using transformations. You guys ready for it? I'll do graph 1 along with you, and then give you a shot at graph 2, and then we'll kind of go back and forth between examples. So for our first function, we have 3 to the x plus 2 plus 1. First thing we want to do is identify our base graph. Now our base in this function is 3, and that's a number that's greater than 1. So the first graph that I'm going to plot is 3 to the x. Okay. Now without any transformations, 3 to the x would go through 0, 1, as well as 1, 3. The left end will be close to the x-axis, and the right end will shoot up to positive infinity. So that would be 3 to the x. There are no negatives in front of our base, so no x-axis reflection to do. But in the exponent, we are adding 2 to x. Any offers as to what that might do? Yep, left by 2 units. So the next graph I'm going to sketch is 3 to the x, but shifted 2 units left. And we can use these 2 points to help us out with that. So 0, 1 is going to move to the left by 2 units. 1, 3 is going to move to the left by 2 units. The horizontal asymptote also shifts left by 2 units, but it'll still lie along the x-axis. It's only when we have vertical shifts that the location of the horizontal asymptote changes. I'm going to go ahead and connect these points in a very similar way is that of 3 to the x, and that would be 3 to the x plus 2. Last but not least, we have this plus 1 at the tail end, and here we can think normal. All right, numbers at the tail end are for vertical shifts, and since it's plus 1, we're going to go up 1. And we'll base this on our most recent graph, which is the green one. We'll take those 2 points, move them up by 1 unit. Now, keep in mind the 1 unit gap. All right. If you're keeping track of the y-intercept, it's now right here at -2, 2. And there's always a 1 unit gap between the y-intercept and the horizontal asymptote. In this case, the horizontal asymptote is going to be underneath the new location of the y-intercept. And if there has to be a 1 unit gap, this means that the horizontal asymptote would now have to have the equation y equals 1. And so basically the horizontal asymptote shifts up by 1 unit because of the value of k. And with that said, we can go ahead and connect those 2 points, the orange one and the light blue one, in a similar shape as our previous graphs. And that would be our graph of 3 to the x plus 2 plus 1. Ain't she a beaut? All right, so how'd that go for you? Did that make sense? You guys have any questions about that? All right, go ahead and try problem 2. 4 to the x minus 1 minus 3. All right, I'm going to start sketching mine out. The base A is 4. And that's a base that's greater than 1. So the first graph I'll do is 4 to the x, which will go through 0, 1, and 1, 4. The left end will be near the x-axis, and the right end will go up to positive infinity. What's our first transformation? Right by 1. Yep, very good. I'll take these 2 points, move them to the right by 1. The horizontal asymptote also moves right by 1, but that's still going to lie along the x-axis. It's 4 to the x minus 1. And what's the last transformation? Down 3. Yep. All right, so I'll take those 2 green points, move them down by 3 units. The horizontal asymptote also has to move down by 3 units. And it's going to cross the y-axis at y equals -3. And how we should know that is that there's the 1 unit gap between the new location of the y-intercept, which by the way is at 1, -2. And we'll go ahead and connect the 2 points and form the ends of our graph. And we have 4 to the x minus 1 minus 3 right there. All right, how you guys doing? Would you like some more? Let's do some more. Now, for some reason, the author likes to present some of the exponential functions in this format, where it's kind of like switched up. The exponential expression and the value of k are swapped with each other. When I see that, I just quickly rewrite it with the exponential expression leading off, which, since we're subtracting it, that's going to make a negative in front of 2/5 to the power of x. And then the 1 is positive, and for that reason, I'll finish this off with plus 1. So negative 2/5 to the power of x plus 1 is the rewrite of the function, and this is kind of in a better format for us to identify those transformations. Now the base is 2/5, which has a decimal as 0.4, so this is a situation where a is less than 1. Okay, so the graph will start out decreasing, and 2 points that would be on the graph of 2/5 to the x would be 0, 1, and 1, 2/5, which I'll go to the right to x equals 1 and then go up roughly halfway. And this will allow us to form the base graph of 2/5 to the x. Now let's talk transformations. You guys noticing something new other than the base?
There's no transformation. Or
What about this right here? The minus sign. Yep, so remember when we have a minus sign in front of the base, that is going to be an x-axis reflection. So I'm going to mirror 0, 1 across the x-axis, and then I'll also mirror 1, 2/5 across the x-axis. And this basically turns the graph upside down. And I just want to point out that the right end of this orange graph approaches the x-axis but never crosses or touches it. So the horizontal asymptote, it does reflect, but it kind of reflects onto itself since it's on the line of reflection. But that would be our graph of negative 2/5 to the x. And there's one more transformation. Any offers on that? It would be this right here, plus 1. So let's take these 2 orange points and move them up by 1 unit. And for that second orange point, I know it's a little weird to shift it up 1 unit since it's not, on a corner point. So here's where it might help to draw the horizontal asymptote first, which gets shifted up 1 unit due to the vertical shift. And that way you know not to go too far when you move up that second orange point. And that would be our graph. All right, any questions so far? I'm going to have you work on number 4. let me point out a couple of things first. The base is e, which is roughly 2.718. Regardless of its approximation, it is greater than 1. And there's also this minus sign, but this time it's in front of x. And you may recall from chapter 3 that when the negative is in front of x, kind of like on the inside of the grouping symbols, that would give us a y-axis reflection. All right, so with that, let me give you a couple minutes to work on the sketch of this graph, then we'll go over it. And then there are going to be some more details that I'd like to include for each of these. All right, so we'll get to that in just a few minutes. All right, here we go. So e to the x is what I'll draw first. 0, 1, 1, and comma 2.7-ish. Then we have the y-axis reflection. So 0, 1 is on the axis of reflection. It's not going to change position, but the point that's in quadrant 1 is going to mirror over to the left and now be at negative 1, comma 2.7-ish. So this will make e to the x turn into a decreasing graph due to that y-axis reflection. And then we have plus 2 at the tail end. So that's a vertical shift up 2 units. Okay, so I'll take 0, 1, shift that up by 2 units, and then I'll take the second point, move that up by 2 units as well. And in addition to that, the horizontal asymptote will move up by 2 units. And a way to remember that is the 1 unit gap, okay, between the y-intercept and the horizontal asymptote. And we'll draw the same shape as e to the negative x, just shift it up by 2 units. All right, is that what you got? Sweet. All right. Any questions so far? All right, so I'm gonna I'm going to request some additional information with each of these, and maybe I'll dub it the Fantastic Four. Um, we're kind of Marvel fans here, and there's just like 4 additional items that I want, and I'm just kind of thinking on the spot here. We'll call it the Fab or Fantastic Four, but basically, I would like some additional details with each of these graphs, specifically the domain, the range, the equation of the horizontal asymptote, and also the new location of the y-intercept 0, 1. Okay, so for domain, don't let this trip you up. Remember, the domain of all exponential functions is all real numbers. It's because these things widen out in both directions forever and ever. As for the range, keep in mind we can use the horizontal asymptote to help out with range. If we look at this light blue graph, which is our final graph, the left end of the graph gets close to the y value of 1, but never achieves it. So for that reason, the lower end of our range is going to be parentheses 1. And if we look at the right end of our blue graph, that goes up to positive infinity, which would help us form the rest of the range, infinity with parentheses. Now the equation for the horizontal asymptote, we already jotted down on our graph. That's kind of a freebie, y equals 1. And then we noted that the y-intercept ended up at negative 2, 2. Okay, so that's what I'm going to start calling the Fantastic Four. And I'm going to give you guys some time to see if you can come up with these results for graphs 2 through 4. All right, so as a reminder, that's going to be the domain, the range, the equation of the horizontal asymptote, and the new location of 0, 1. All right, and while you guys are working that out, I'll just go ahead and set up the rest of the Fantastic Fours here, and then we can go over the results shortly afterwards. All right, let's go over the answers here. So the domain for the function given in 2 is going to be all real numbers. Anybody want to offer the range? Perfect. Nicely done. Yep, the left end of the graph approaches the y value of -3. The right end goes up to infinity. Horizontal asymptote, kind of a freebie here, y equals -3. And then where did 0, 1 move to? 1, -2. All right. Let's move on to number 3. Domain is all real numbers. The range, since this graph is upside down, the left end is going down to -infinity. So we'll start the range with that. And the right end of it approaches the y value of 1. So perfect. -infinity, comma 1, parentheses on both. Y equals 1 for the horizontal asymptote. And where did 0, 1 move to? Yeah, right here at the origin. I said it was going to get cooler, right, Sarah? Have I delivered on that promise? All right, so the domain is all real numbers for, all right, cool, thank you. Yep, it's going to get even more exciting after this. You just wait. So the domain is all real numbers for number 4. The right end of this graph approaches 2, whereas the left end goes up to positive infinity. So on the lower end of the range will be 2, and the upper end of the range will be infinity. Horizontal asymptote y equals 2. And then 0, 1 ended up at 0, 3. All right, so that's the tour de transformations with exponential functions. Do you guys have any questions for me about this? All right, well, let's move on to our last topic in chapter 6.3. Any of y'all like to go fishing? If you do, this property is for you. All right, so in just a second, I'm going to introduce what I call the fishing lure technique. But overall, just kind of, in a broader perspective, our last topic for this section is going to be solving equations where the variable is in the exponent. And these are kind of like the basic ones. As we get a little further in chapter 6, we'll have some more advanced types of these equations. So that's why I'm calling it like a first encounter. And what we're going to use to solve these special types of equations is what's called the one-to-one property of exponential functions. And it basically says this: if you can rewrite each side of your equation using the same base, then you get to form a second equation using the exponents. And by the way, this is why I call it the fishing lure technique. Stated differently, equal bases implies equal exponents. So when we solve these, we're going to want to rewrite each equation so that it's one base raised to a power, and then on the other side, the same base raised to a different power. And if we can get it that way, then we're going to jump to a secondary equation where we set the exponents equal, and that is what allows us to solve for the variable. All right, case in point, let's look at example part A, where we've got 2, and in its exponent, which I'll surround in parentheses, just so that we know that all of that's part of the exponent, is 2x minus 1, and then on the right-hand side we got 4. So the left-hand side is already written in exponential format. It's using a base 2. So the trick is to see if you can rewrite 4 as a power on 2. It's 2 squared. Yeah. So I'm going to leave the left-hand side alone, but the right-hand side I'm going to rewrite as 2 squared. And here we have equal bases, which means we get to set the exponents equal. All right. So by setting the exponents equal to each other, which we can only do if the bases are the same, we get to solve for x. We can add 1 to each side, 2x equals 3, divide by 2 to get x equals 3 halves. And there it is. Let's look at part B. We got 4, and in its exponent, the expression 2x minus 1 again. And then on the right, we have 8 to the power of x, which, although not necessary, I'll put in parentheses. Each side involves an exponential expression. The left-hand side has a base 4, and the right-hand side has a base 8. So because they're different numbers, we can't just set the exponents equal to each other. We can only do that once the bases are the same number. Yeah, so that was going to be my question. Yep. Thanks, Avita. You can rewrite both of the bases using the same number. Specifically, you can use a base 2 to rewrite 4 and 8. So much like in the last problem, I'm going to rewrite this 4 as 2 squared, but I'm going to put that in parentheses, and you'll see why in just a minute. And outside of the parentheses is the exponent of 2x minus 1. And on the right, let's rewrite 8 as 2 cubed, raised to the power of x. Now before we go further, I want to do a little recall statement. Does anybody here know how to simplify something like x cubed squared? If we wanted to write this as x to just 1 power, what would we have to do with 3 and 2? Yeah, you'd have to multiply the 3 and the 2 together to get x to the 6th. So basically, when you raise a power to another power, you have to multiply. And the reason why I'm taking this little detour is because that's exactly what's happening in our current equation. We have a power of 2 being raised to a power of 2x minus 1. We're going to have to multiply those two together, and we'll also have to multiply the 3 and the x together. Now, when we do 2 times 2x minus 1, that is technically going to require distribution. And so a simplified version of this power is going to be 4x minus 2. And then on the right-hand side, we'll have 2 to the power of 3x. Does that make sense? And just like that, we have equal bases, which means we get to set the exponents equal to each other. Okay, so 4x minus 2 equals 3x. And in the interest of time, we end up getting x equals 2 as our answer. Let me have you try out part C. It's very similar to part B. We'll go over it in just a couple minutes, and then I'll help us navigate our way through part D. Okay. Yeah, very good. X equals 6. Yep. Yeah. Yep, we're going to see that in just a moment. What I would do is rewrite both the 9 and the 27 using a base 3. 9 is 3 squared. That's getting raised to quantity negative x plus 15. And then you could rewrite 27 as 3 cubed. And that's getting raised to the power of x. So much like in the last problem, we can multiply the exponents together. Distribution required on the left, direct multiplication on the right. So we'll have 3 to the power of negative 2x plus 30 equaling 3 to the power of 3x. And same bases means that we can set the exponents equal. And this would land us at x equals 6. Now, I didn't mean to rush the algebra there, but I do want us to get to part D. In order to tackle this, I'll have to do another recall with y'all. What if we wanted to use exponents of 2 and 3 in the following way instead? Let's say we had x cubed, and instead of squaring it, we wanted to multiply x cubed to x squared. Would we still multiply the 3 and the 2 together, or would we do something different? Yep, you'd have to add them together. All right, and that would give us x to the 5th. So when we multiply exponential expressions with the same base, we end up adding the exponents. And you can probably see where I'm heading with this, with the equation in part D. We're multiplying two exponential expressions with the base e, and we can condense that to a single base e provided that we add the exponents together. That will end up giving us e to the power of x squared minus x equaling e to the 12th. Make sense? If so, we have equal bases, which means that we can set the exponents equal. And Tim, you're right on the money with this. We end up getting a quadratic equation, and the easiest way to solve one is to use factoring, which would require setting maybe the right-hand side to 0. And if the left-hand side factors, that's going to give us our quickest route to answers. But if it doesn't factor, then quadratic formula. Fortunately, this does factor as x minus 4 times x plus 3. And upon setting each factor equal to 0, we actually get two answers for x. X equals 4 and x equals negative 3. All right, so any questions about this example or any of the others? Oh man, we made it through chapter 6.3. I'm going to upload a video solution to part A of this section, this one right here. And in the video solution, I'm going to show you how to solve this graphically. Okay,